The complement system refers to a group of plasma proteins called the complement proteins, which are produced in the liver and act collectively to help destroy pathogens. Think of them like a little militia that complement the work of antibodies. There are actually three complement pathways: the classical pathway, called that just because it was discovered first, the alternative pathway that was found second and is always at work, and the lectin binding pathway, which was found third when folks got more descriptive with their naming. So let's start with the proteins that make up the classical pathway: C1, C2, C3, C4, C5, C6, C7, C8, and C9. Pretty easy, right? Now, these were numbered in the order they were discovered, but not in the order that they function. Generally speaking, each complement protein is normally inactive, and it becomes activated when it's cleaved. In other words, when some part of it breaks free. Kind of like how a fire extinguisher isn't active until a pin is pulled out. Now, in the classical pathway, things start out with C1. C1 has three components: C1q, C1r, and C1s. It has 6 C1q subunits, which are able to bind to the Fc portion of an antibody when it's bound to an antigen. Each C1q can bind to one antibody-antigen complex. So technically, each C1 molecule can bind 6 antibodies. Both the C1r and the C1s subunits are both enzymes called serine proteases. C1q has 0 enzymatic activity, and typically the serine proteases C1s and C1r are hidden, so they can't perform their enzymatic activity. And this is all tied together in a calcium bow, so when there's a lack of calcium, C1 is also lacking. When 2 or more of the C1q portions bind to the Fc receptors of 2 or more antibodies that are bound to antigen, it causes a conformational change of the C1 molecule which twists, exposing the C1s and C1r serine protease sites. Kind of like taking the safety cover off a pair of scissors. This allows C1r to cleave C1s, activating the C1 molecule. The activated C1 cleaves C4 into C4a and C4b. C4a floats away, but C4b binds to the surface of the pathogen. C1 also cleaves C2 into C2a and C2b. This time C2b floats away, and C2a joins C4b on the surface of the pathogen, forming a protein complex called C4b2a, or C3 convertase. C3 convertase cleaves C3 into C3a and C3b. Now, this is the step that really amplifies things. That's because a single C1 can generate maybe 10 C3 convertases, but a single C3 convertase can cleave over 1,000 C3 proteins per second. And this enzyme stays active for about 2 minutes, so you'll end up with a lot of C3b really quickly. Now, C3b is also called opsonin. And in general, opsonins are awesome because they help phagocytes get a firm grip on bacteria. Normally, bacteria have an anti-phagocytic capsule, which makes them slippery and hard to grab. Opsonization is the process by which pathogens are coated with molecules so that they can be more easily picked up by phagocytes. Imagine trying to pick up a slippery meatball with your fingers versus stabbing it with a fork and then just having to pick up the fork. Opsonization also makes it easier to eat meatballs faster too. In this case, C3b is serving as that fork. Once there's a certain amount of C3b made, some of the C3b proteins come and bind really close to the C4b2a, or C3 convertase, and turn it into C4b2a3b protein complex, which is called C5 convertase. The C5 convertase cleaves C5 into C5a and C5b. C5b binds to C6, C7, and C8. And together these 4 proteins begin to penetrate through the pathogen's cell membrane. They're joined by small groups of C9 proteins, which help form a channel straight through the membrane of the pathogen. So this cluster of C5b, C6, C7, C8, and C9 proteins form the membrane attack complex, or MAC, which is what creates a hole in a bacterial cell membrane. Alright, next up is the lectin binding pathway. This pathway has one key difference from the classical pathway. Instead of being triggered by an antigen-antibody complex in C1, the lectin binding pathway uses a protein called mannose binding lectin protein, which is a protein that binds mannose, a sugar found on the surface of many bacterial surfaces. Mannose binding lectin protein is similarly shaped to C1 and can cleave C4 and C2, helping to establish C4b2A or C3 convertase. From that point on, things are the same as the classical pathway. Finally, there's the alternative complement pathway. Now, although C3 gets cleaved into C3A and C3b by C3 convertase, this also happens in the absence of the enzyme at a very slow rate. That means that there's always small amounts of C3b floating around and binding to any bacterial surfaces that it might encounter. Now, there are proteins called factor B and factor D that are also in the blood. Factor B will bind to C3b on the bacterial surface, and when it does, it allows factor B to be cleaved by factor D, which is always active. So factor B becomes BA and BB. The BA will float off, but BB will stay associated with C3b. This complex has its own cleaving abilities. It's a C3 convertase, so it'll cleave C3 into C3A and C3b, thus acting as an amplification step. And at this point, the pathway will follow the classical and lectin binding pathways, building the MAC. But because C3 can spontaneously get cleaved and trigger this alternative pathway, it has to be carefully regulated. And that's where C1 inhibitor comes in. C1 inhibitor will dissociate factor BB from C3b, thus shutting down the alternative C3 convertase. Factor H also acts as a cofactor for another factor, called factor 1, which breaks C3b into inactive C3b or IC3b. IC3b is still a potent opsonin, but it has no enzymatic activity and cannot propagate the alternative complement pathway. So all three pathways start out a bit differently, but they all end the same way, with a membrane attack complex. And this again is a protein complex that creates a hole in a bacterial cell membrane, which effectively destroys mainly gram-negative bacteria. But the various complement fragments end up playing an important role. In addition to C3b serving as opsonins, other fragments like C5a and C3a also act as chemotaxins, which recruit neutrophils, eosinophils, monocytes, and macrophages to the site of inflammation. C5a and C3a are also anaphylatoxins, which means that they help basophils and mast cells degranulate, releasing pro-inflammatory molecules like histamine and heparin into the area. This can cause contraction of the smooth muscles, as well as bronchial constriction and increased vascular permeability. Finally, because C1, C2, C3, and C4 are all involved in removing antigen-antibody complexes, individuals that lack any of these proteins can experience a lupus-like illness, as well as chronic renal disease and repeated infections. Individuals who are deficient in C5, C6, C7, or C8 suffer from repeated Neisseria infections and are at higher risk for developing gonorrhea or meningitis. Interestingly, individuals who are deficient in C9 seem to have no problems, because C5, C6, C7, and C8 can lyse a bacterium all on their own, with C9 being icing on the cake. Alright, as a quick recap. There's the classical, lectin binding, and alternative complement pathways. The classical pathway starts with an antibody bound to a pathogen. The lectin binding pathway starts with mannose binding lectin protein binding mannose. And the alternative pathway is always active, because there's always some C3 being cleaved into C3a and C3b. All three pathways end with the creation of the MAC, which will kill a pathogen. And along the way, there's creation of C3a and C5a, both acting as chemotaxins and anaphylatoxins, and C3b acting as an opsonin, which will help phagocytes grab and destroy pathogens, just like forks on a meatball.